Welcome. In this short video, we make new functions out of old functions. And there are basically two ways to do this. One is by elementary combinations like addition, subtraction, division, and multiplication. And the other is by compositions. And if I say compositions, I unfortunately do not mean musical compositions. I mean compositions of functions as they arise in mathematics. So, let's look at the elementary combinations first. I assume I have two functions, a function f of x which has a domain a, and a function g of x which has a domain b. And I look at f plus g. So f plus g then is a new function which is defined as f of x plus g of x. So that's trivial, but the domain is a little bit interesting. So what is the domain? The domain are all values of x which I can substitute into this new function here. To substitute it here, I need to substitute it here and here. So the value x must be in the domain of both, of f and g. So which means the domain here is the intersection a intersected with b. Now, the similar is true for the minus sign. I didn't write this down extra. For the product function fg of x is f of x times g of x. And same story, the domain is the intersection of both domains because x needs to be able to be substituted into both. Similar for the ratio, f divided by g is f of x divided by g of x. However, here we need to ensure that g of x is not 0, because we know we can't divide by 0. So here we write the domain is a set of all points x in a intersection b, so that g of x is non-zero. And so this way we can already create a whole bunch of different functions. Okay, let's look at one example. We have the function f of x is sine x, the domain is all real numbers, and the function g of x is x squared minus 2, and the domain is all real numbers, and I'm interested in the ratio f divided by g. So this is a new function f divided by g of x, which is sine x divided by x squared minus 2. Now the domain, first you might think it's all real numbers, however, you see the denominator could be 0, and we cannot divide by 0. So what we have to do is we take all real numbers, but then we may restrict that x squared minus 2 is not equal to 0. And first you can just write it down in this form. Just keep life simple. But then we can simplify this set, which is all real numbers, so that x is not equal to plus or minus root of 2. So that is the domain of this function. Now let's come to composition of functions. So it is a little bit like you take maybe one function, which is an old car, and you take another function, which is symbolized by a super duper engine, kind of a cool engine, and you combine them to get something new. So you get kind of a cool beetle coming out of this. And this is what we would like to do with functions now. So we take one function and substitute it into a different function, and together they make a new, maybe even cooler function. This is called composition, and it is symbolized by this circle. So f circle g is the function f, where I substitute the function g. Or say it the other way, you first substitute x into g, and then you substitute everything into f. This is really called f composed with g, but it is much easier to say f after g, because in particular here it is f after g then applied to x. Now the domain is interesting, right? First of all, you need to be able to substitute x into the function g. So we take x from the domain of g. But then in addition, g of x, whatever you get, must be able to be substituted into f. So g of x must be in the domain of f, which is a. So that is the domain of a composed function. As example for composition, I use already a composition of three functions. So let's f to be cosine, g of x is 1 divided by x, h of x is x plus 2. So let's try to put one into the other right from the start. So I said this should be read as f after g after h. So let's start on the outside and write down what f is. F is cosine of x. But then instead of x, I introduce the function 1 over x, which is g. But then again, g is evaluated at h, so I should write 1 x plus 2. So we have the new function cosine of 1 divided by x plus 2. Now let's look at the domain. So the domain of this function is then all real numbers, but we need to ensure the denominator is not equal to 0, so we can't have x to be minus 2. Another example, which is quite interesting, is this one here. So let's look at the composition of f composed with g composed with h. So here's a little mistake. And outside we have the root of 2 minus something, so we make a very long root because we don't know yet what is inside. And then instead of x, we use the function g of x, which is 3x plus 5. But then g is evaluated at h. H is x squared. So you should really sit down and try to do it yourself to come up with this formula step by step. We can multiply out what is inside the square root, so we have 2 minus 3x squared minus 5, which is root of minus 3 minus 3x squared. Oh, now we notice something very interesting. So minus 3 is always negative, of course, and x squared is a positive number, so minus 3x squared is negative. So the whole thing inside the square root is always negative. And this is a problem, because negative numbers we can't take the square root. So the domain of this function here is what? Is empty. There's no function, there's no value x which I can substitute into this function. So in other words, I could say the function is not well defined. So see where we started. We started with the function f, g, and h. They all look like normal functions, which we use all the time. However, if you have a funny combination of these functions, you might actually get something which doesn't make sense. Now, one more example, since we are doing so well. So look at the composition of f after g after h, where f is a square root, g is sine of x, and h is pi x divided by 2. So we have square root of sine of pi x divided by 2. The sine function becomes negative occasionally, and then again we can't take the square root. So we need to find out where is the sine function of pi x over 2 negative. And to do this, I do this graphically, and I start with plotting just the sine function. This is something I'm pretty good at. I memorized how to do the sine function. So this is sine of x, and this is x. And I know the zeros are at pi, and at 2 pi, and at 0, and at minus pi, etc. Right? So this is the sine function. But now what I really need is this modified function of sine of pi x divided by 2. So let's do another graph where I plot this new function, which I really have here. So sine of pi x divided by 2. Again, I expect an oscillation, but I'm interested now where is this function equal to 0. So look at pi. So here the sine function is 0 when the argument is equal to pi. Now this argument is equal to pi when x is equal to 2. Okay, so then I indicate the 2 here, and I have already my first loop. Now the next point where it is 0 is 2 pi, which corresponds to x to be equal to 4. So I indicate a 4 here, and I know the sign goes this, and then of course it continues with 6 here, minus 2, minus 4, minus 6, etc. Right? So, so this is this new function, sine pi x divided by 2 looks like this. It is the same way as a sine. However, the zeros are a little bit stretched out. Okay, and now I can wonderfully, easily look at the domain of this function. So the domain is, well, I can only use the positive bits. Okay, so I can use this bit, and this bit, and this bit, but I cannot use the lower bits where the sine function is negative. So the domain is, actually I start with dots because it continues to the left and to the right. And then the first interval here I see is minus 4 to minus 2. And then union with the interval from 0 to 2. Union interval from 4 to 6, etc. Okay? So we get a disjoint union of intervals, and between those intervals the function is not defined. On those intervals the function is defined. Let me summarize. So to combine functions out of given functions, First, we have elementary combinations like addition, subtraction, multiplication, and division. We notice for division, we need to make sure that g is not 0, otherwise we get a problem here. Then we heard about compositions, and at some point, a student read FOG to be fog, and he came to me and said, "What does fog stand for?" I'm not quite sure if he was kidding or not, but anyway, so I hope you remember that FOG stands for F composed with G and not for fog, and so I hope that this little video can help to lift the fog of mathematics for you.